Today's module is an introduction to biological molecules. Module 5 will be covered in two videos. In the first video, we will review ionic and covalent bonds. We will also review the concepts of electronegativity and bond polarity. Then, we will introduce hydrogen bonds as a new and important concept. After that, we will discuss solubility and inorganic acids and bases. We will finish the first video by discussing biological reactions. In the second video, we will investigate 4 different biological molecules. The learning outcomes of the first part of Module 5 are: differentiate between ionic and covalent bonds, identify hydrogen bonds, determine solubility of compounds, identify inorganic acids and bases, and identify the biological reactions. As mentioned in the introduction, we will start with a quick revision before we move on to new content. Chemical bonds are the forces that hold atoms together. The two important types of bonds we will cover are ionic and covalent. Ionic bonds occur between metals and nonmetals. Here there is a complete transfer of electrons from one atom, which then forms the cation, to another, which forms the anion. Take sodium chloride as an example. Sodium loses one electron, therefore gaining a positive charge, and chlorine gains the electron and forms the negatively charged chloride anion. The ratio in sodium chloride is 1:1. Solid sodium chloride forms crystals where every sodium is surrounded by 6 chloride ions. Likewise, each chloride ion is surrounded by 6 sodium ions. In this table, you can see some of the important ions and ionic compounds in our body. For example, the calcium ion is very important in muscle contractions. However, you don't need to memorize this table. Covalently bound atoms share electrons to form molecules. Two elements come together and share their valence electrons due to overlapping of the orbitals. This forms the covalent bond. For example, hydrogen with its single electron can fill its valence shell, shell 1, by sharing a pair of electrons with another atom. When it shares with another hydrogen atom, it forms molecular hydrogen, H2. Carbon has 4 electrons in its valence shell, but needs 8 to achieve stability. Hydrogen has 1 electron, but needs 2 to achieve stability. By forming a molecule of methane, CH4, a carbon atom shares 4 pairs of electrons with 4 hydrogen atoms. Multiple bonds occur to fulfill the octet rule around elements when there is not enough electrons left. The elements can then form multiple bonds by sharing 2 or 3 pairs of electrons between 2 atoms. See the examples: O2, carbon dioxide, C2H4, N2, and HCN. A double bond is stronger than a single bond, but not twice as strong. Triple bonds are stronger than double and single bonds. This means we require more energy to break a triple bond than we do for double or single bonds. In biological molecules, it is common to see carbon-carbon and carbon-oxygen double bonds. Electronegativity is the strength or desire of an atom to pull electrons towards it. Fluorine, chlorine, oxygen, and nitrogen are the strongest electronegative elements in the periodic table. Electronegativity affects the nature of the bond between elements. When the two atoms in a covalent bond share the electrons equally, the bond will be nonpolar covalent, and the molecule is nonpolar. For instance, in O2, there is an equal sharing of electrons. However, when one element has a higher electronegative value, the atoms do not share the electrons equally, which might cause a polar covalent bond. For example, in water, the oxygen is more electronegative than the hydrogen, so the electrons spend more time around the oxygen than the hydrogen. This results in a partial negative charge around the oxygen and a partial positive charge around the hydrogen. In terms of geometry, molecular shape and the relative electron attracting abilities of atoms determine whether a covalently bonded molecule is polar or nonpolar. The water molecule has a bent shape, similar to a boomerang. The electron pairs are not shared equally, but spend more time in the vicinity of the oxygen atom, which causes slightly more negative charge around it. The electrons spend less time around the hydrogen, leading to a partial positive charge. So water has two poles of charge, therefore it is a polar molecule or dipole. Now we will cover a new and very important concept, the hydrogen bond. A hydrogen bond is a force of attraction or bridge between two molecules. For hydrogen bonds to occur, there are four criteria that should be met. Firstly, hydrogen bond is a force of attraction that involves two molecules. Secondly, the first molecule should contain a hydrogen atom that is bonded to an element with high electronegativity, either a fluorine, oxygen, or nitrogen. Thirdly, the second molecule should contain an element with high electronegativity, such as a fluorine, oxygen, or nitrogen. Finally, the bridge occurs between the hydrogen from molecule 1 and the electronegative element from molecule 2. Hydrogen bonds are represented by a dotted line. Let's apply the criteria to the example of water and see if hydrogen bonds can occur. The first criteria says that hydrogen bond is a force of attraction that involves two molecules. To meet the first criteria, we need our two water molecules. The second criteria states that there should be a hydrogen atom that is bonded to an element with high electronegativity in the first molecule. We can see that the hydrogen is bonded to oxygen, which has a high electronegativity. The third criteria mentions that the second molecule should contain an element with high electronegativity. You can see an oxygen atom in the second molecule. As all criteria are met, then a hydrogen bond occurs between the hydrogen from molecule 1 and the electronegative element, the oxygen, from molecule 2. So hydrogen bonds are more like intermolecular attractions than true bonds. Hydrogen bonds are weak compared to ionic and covalent bonds. They do not bind atoms into molecules, but rather they establish important links between molecules such as water, or between different parts of a large molecule such as a protein or nucleic acid. Even though a single hydrogen bond is weak, large molecules such as proteins may contain hundreds of these bonds. Collectively, these hydrogen bonds provide considerable strength that maintains the three-dimensional shape of large molecules such as proteins. For example, water and methane, CH4, have similar atomic masses. However, the melting and boiling points for water are much higher than those points for methane. The reason is that water can form hydrogen bonds between the molecules, but methane cannot form these bonds. Let's look at another example and see if hydrogen bonds can occur between ammonia molecules. The first criteria says that the hydrogen bond is a force of attraction, or bridge that involves two molecules. To meet the first criteria, we need two ammonia molecules. The second criteria is met as the hydrogen is bonded to nitrogen, which has a high electronegativity. The third criteria is also met as there is a nitrogen atom in the second molecule. As all criteria are met, then a hydrogen bond occurs between the hydrogen from molecule 1 and the nitrogen from molecule 2. Now let's study the concepts of solubility, acids, and bases. First, we'll talk about solubility. If you put 1 spoon of salt in water, it will dissolve. However, sand will not. To understand why we can dissolve certain substances and why we can't dissolve others, we will cover some terminologies first, then we will investigate what affects solubility. A solution describes a system in which one or more substances are dissolved in another substance. The solute refers to the compound that dissolves in the solvent. So in our example, the solute is the salt, the solvent is the water, and together they make the salty water, which is the solution. So we can define the solution as the combination of the solute and the solvent. The solubility describes how much of the solute will dissolve in the solvent. There are several factors that influence the solubility. To study those, we will look at the example of preparing a cup of instant coffee. The first factor is temperature. If you try to dissolve instant coffee in cold water, it will take more time to dissolve compared to using hot water. The second factor is concentration. Dissolving 1 spoon of instant coffee will be much easier than dissolving 10 spoons. Particle size is also a factor. For example, fine powdered coffee dissolves much easier than big chunks of coffee. The fourth factor is agitation or stirring. Stirring the coffee powder will make the process faster. Now the main factor that determines the solubility is the polarity. The term like dissolves like means polar solutes and polar solvents mix together very readily. For example, salt and water are both polar, so they mix together easily. Likewise, non-polar solutes mix easily with non-polar solvents. Oil and petrol mix easily as they are both non-polar. However, oil and water don't mix because oil is non-polar and water is polar. There are 2 terms that we often use to describe the solubility properties of a solute in water. The term hydrophilic means water-loving, and hydrophobic means water-hating. They are very similar to the terms polar and nonpolar. So hydrophilic molecules tend to be ionic or polar compounds, and they interact with or be dissolved by water and other polar solvents. Hydrophobic molecules tend to be nonpolar and thus prefer other nonpolar solvents like petrol. Those terms can refer to a molecule or part of a molecule. For example, we will see that in proteins there are hydrophilic parts and hydrophobic parts. After we talked about the terms related to solubility, let's go back to our example and discuss how we can dissolve the salt in water. We know that sodium chloride is an ionic compound, so sodium has a positive charge and chloride has a negative charge. We also know that water is a polar molecule. So when we add salt to the water, you can see that the water molecules surround the sodium and chloride ions as explained in the diagram. The sodium ions will be surrounded by the oxygen atoms that carry partial negative charge. Likewise, the chloride ions will be surrounded by the hydrogen atoms that carry a partial positive charge. Now we covered solubility, let's look at acids and bases. Acids and bases form ionized species in water. For example, hydrochloric acid forms hydrogen ions and chloride ions in water. An example of a base is sodium hydroxide, which can also be ionized in water to turn into sodium ions and hydroxide ions. Lots of our food is acidic, like vinegar and lemon juice. We covered previously that a hydrogen atom has one proton, no neutrons, and one electron. So when it loses that electron, it forms a hydrogen ion with one proton only that carries the positive charge. For this reason, we can use the term proton instead of hydrogen ion. There are several definitions of acids. The most useful is that acids can donate hydrogen ions, the proton, so they are called proton donors. Bases are the opposite of acids. They taste bitter and feel slippery or soapy. Bases are proton acceptors. For example, the hydroxide ion is a base and is able to accept a hydrogen ion to form a water molecule. Another example of a base is ammonia. It can accept a hydrogen ion and forms the ammonium polyatomic ion. To ensure homeostasis, the intracellular and extracellular fluids must contain balanced quantities of acids and bases. Even a small deviation from the normal limits of H+ and OH- concentration greatly disrupts body function. We can express the concentration of hydrogen ions and hydroxide ions on a scale called a pH scale. The midpoint of the scale is the pH 7, which is considered neutral. So we have an equal concentration of hydrogen ions and hydroxide ions. When the pH is less than 7, then we have an acidic environment, and when it is greater than 7, it is a basic or alkaline. Please note that the term basic means the opposite of acidic in our context and doesn't mean simple. So when we say a basic solution, we mean the pH is more than 7 and not that the solution is simple. The pH scale is a logarithmic scale, so each change of one pH unit represents a tenfold change in hydrogen ion concentration. For instance, a solution of pH 6 is 10 times more acidic than a solution with a pH of 7. This table shows some examples of substances with their pH values. As you can see, gastric juice is very acidic. Water is considered neutral. Our blood is also neutral and is a very tight pH range between 7.35 and 7.45. Now let's discuss the different types of biological reactions. In a chemical reaction, one or more reactants get converted to one or more products. There are different types of biological reactions that occur in the body, and the main types are synthesis, decomposition, exchange, and reversible reactions. The first type are the synthesis reactions. A synthesis reaction can happen when two reactants combine together to form a larger molecule. The reactants can be atoms, ions, or molecules. Sometimes it is called an anabolic reaction, which means building up larger molecules. We can express this as A plus B combined to form AB. Let's take an example. Hydrogen gas combines with oxygen gas to form water molecules. Anabolism reactions generally require the input of energy. An example from our body is the building of proteins from amino acids. Decomposition reactions are the opposite of synthesis. So, a large molecule splits into smaller parts, such as atoms, ions, or molecules. Sometimes it is called a catabolism reaction. We can express it as AB splits up into A plus B. Catabolism reactions generally release energy. For example, large carbohydrates like starch break into simpler sugar units and release energy in that process. Many biological reactions are exchange reactions. They consist of both synthesis and decomposition. So when we have multiple atoms in the reactants, the atoms rearrange, similar to changing partners in dancing, to produce new products. For instance, if the reaction starts with AB plus CD, they swap and the result is AD and CB. Notice that the anion from the first molecule will exchange position with the anion from the second molecule. Likewise, the cation from the first molecule will exchange position with the cation from the second molecule. So B can only exchange with D, C can only exchange with A. A and C cannot come together as they are both cations. For example, HCl, an acid, plus sodium hydroxide, a base, will react together so that the sodium will end up with the chloride and produce sodium chloride. The hydrogen will end up with the hydroxide and form water. Important examples of exchange reactions involving water are condensation reactions and hydrolysis reactions. Condensation reactions are very important to create larger polymers and longer chains. This happens due to the loss of a water molecule in the reaction between two molecules. Each molecule contributes part of the H2O. For instance, you can see in the diagram that the first molecule provided the hydrogen and the second provided the OH. In this way, the monomer units can join together to form a growing chain, like that shown in the diagram. Hydrolysis reactions are the opposite of condensation reactions. The term hydrolysis comes from two parts, hydro, which means water, and lysis, which means to cut. So we add a water molecule to the polymer to split it into two smaller units. Hydrolysis and condensation reactions are important in the synthesis and breakdown of biological molecules, such as building up carbohydrates and proteins from their building blocks, or breaking down these same molecules. Some reactions happen in only one direction, that is, from left to right, so we use one arrow in these reactions. Other reactions are reversible, so the forward and reverse reactions can happen at the same time. We use two half arrows pointing in opposite directions to represent this. Some of these reactions require special conditions. For instance, water is necessary for the forward reaction. For the reverse reaction, we need heat. We usually write these special conditions above and below the arrows. This is the end of Part 1 of Module 5. Please proceed to Video 2, which covers the different types of biological molecules.